All right, good afternoon, everyone. Thanks for coming. And today we're happy to have Dr. Li-Wei Kuo from the Department of Earth Sciences at National Central University in Taiwan. So his main focus is rock mechanics and fault zones. And so we invited him here to show us some of the experimental setup that we're interested in. And hopefully we can get some insights from his setup. And let's see how it goes. And I think we will have a lot of questions for you. So it's welcome. Yeah.
So I'm Li-Wei, and if you have any question, just stop me. So today I would like to share something from my research, and they are all relevant to big earthquake. And before I go to the presentation, I would like to thank my collaborators in this study. There are so many helpers to contribute to this research. Without their help, we cannot have this publication. And today we will have five sub-topics. I would like to start with earthquake fault and frictional power density, which is Earth Science 101 or Physics 101. And then I will talk about some evidence from two big earthquakes. One is from Taiwan, Chichi earthquake, and then one is from Winter earthquake, it's 2008. And then I would also like to introduce what do we have or what we have developed in the last 10 years, and then one take-home message. So what is an earthquake? That's something I would like to explain by this kind of cartoon. So you can see the people pushing a box. And if you come closer to the cartoon, you can see this kind of movement is relevant to stress accumulation and the stress release. And in that case, the box will move along the ground. That's a kind of, we can refer this as a fault phase. So that means for an earthquake, you want to generate an earthquake, you need to have a stress build up, and then you also need to have a weakening mechanism to make the box move. So if you come much closer to that box, you can realize they actually have a lot of asperity between the box and the ground. And once you have some small, fast slip on the interface of the asperities, you will generate small earthquake. And we can image that kind of stuff in the outcrop. So you can assume there's a pre-existing fracture in the rock. And after an earthquake, you will see a slip. And in the outcrop, you can see exactly the same thing, like this. So I would like to introduce the first term. It is the physics 101 called friction coefficient. And the friction coefficient in this case is shear stress over normal stress. So in this outcrop, you can think that the shear stress is kind of resistance you need to overcome to push the box the leftward or rightward. Another physics term is called frictional work. And if you generate work, we used to use shear stress times displacement. That's some kind of work or mechanical work we usually mention for physics. But for earthquake physics, the most important parameter was also mentioned here is called power density, frictional power density. And the frictional power density is shear stress times velocity. So in this case, if you have very large velocity, you will generate very high frictional power density. And the high frictional power density will drive some thermally activate process on this fault surface. So that is something we want to highlight today. And there is an exceptional case called Shuto calculi. It's Giulio Di Toro's paper. And in this work, you can see how high frictional power density contribute. Well, I stop here and expand that in detail. So you can see there are two rock cylinder in the central part of this video, and one rock cylinder was pushed rightward, and another side will be rotate. Sorry. So the movement in this apparatus is trying to mimic fault rupture propagation because they have very large displacement during the earthquake. So in this case, they try to apply to high power density. So during shearing, you can see that high frictional power density can melt rock. Okay, so there's something you can find after big earthquake at very deep depth. But how this kind of process contribute to frictional behavior? So in the right panel, you can see exactly the same apparatus, but the video was captured by very high frame video. So 1 second have 1,000 frames. So you will see a very slow motion movement. And in the right part of this diagram is shear stress over time. So shear stress, you can refer this as a friction coefficient. So in that case, you can see what happened during shearing and how the mechanical response during while time. So in this case, you can see in the beginning of shearing, you have to overcome some static friction, and then you will have power of the powder extrude out, and you will also see some melt patch along the interface. But once the melt layer fully covered the interface, the friction dropped down. So in that case, in Julia's science paper, they mentioned the rock melt can lubricate foam. And that kind of lubrication can make the rock friction from 0.678 down to 0.1. So they are pretty slippery during earthquake. So today I would like to show everything relevant to frictional power density and the relevant thermally activate process. So this is the case from rock samples. So I would like to talk about something relevant to ECDP and Chichi earthquake. And in 1999 Chichi earthquake, was a huge earthquake happened in the northern part. The magnitude is 7.6, and the fault was ruptured from south to north. The surface rupture is about almost 100 kilometers, so it's huge rupture. And from south to north, you got a very large rupture. In addition, you can also observe very large displacement in the northern segment of the fault. So you can see the color over here. You can see that some red color and the orange color. So that.
What's that scale bar?
The scale bar is meter. So from 0 to 20
Meters.
meters
Okay. That's a displacement of the fault.
of the fault. Yes. So on the so this here you can see in the northern segment of the fault, you have 10 meters of lift in the surface, but in the southern part is just dozens of centimeters displacement. After that earthquake, we visit several outcrop along the river, try to capture some geological evidence preserved in the fault, thermally driven reactions. We visit a lot of rivers, Skajia River, Dali River, and Puch River, and Wu River. Unfortunately, we analyze all kind of clay gouge material, and we found nothing preserved in the gouge, clay gouge. It's weird, you know. You see something uplift and slip for a long period of time, but you observe no evidence relevant to frictional heat, even though you have 10-meter displacement. So there's something weird. After that, after 6 years later, we have a deep drilling project. So we try to hit the maximum displacement at the depth. So we check here. There's a the pointer is gone. So you can see here. We have outcrop constraint over here, and we did a lot of reflective seismic profile, try to make sure the active fault zone through the depth. And then we drill in that cross section. So, and we expect that we can hit the active fault zone at 1 kilometer at depth. And this is the outcome. We have two borehole. One is hole A and one is hole B. And we're coring from 500 to 2000 meter for hole A, and the hole B is 900 to 1300 meter. And within the coring, we observe a very dark gouge layer within the light gray gouge layer. And that is a very interesting thing because there is not other place found this kind of phenomenon. Another geophysical data, we conduct logging data, and we observe some residual heat along that borehole in exactly that interval. So that kind of evidence suggests us there's a frictional heat generate, even though you have even after 6 years, you still got very tiny residual heat observed. And then
what's the indicator for residual heat?
sorry,
What's the indicator for the residual?
0.08 degrees,
Yes.
right? Measured.
Oh, you measure the temperature directly. Okay.
logging data.
Yeah.
Yeah, over here. Okay.
Pretty small.
Yes. And yeah,
Yeah.
the temperature is about 0.06 because they did a lot of measurement. So they make sure this kind of residual heat is from rock instead of fluid. Okay, so that's a very important thing. And the second thing is the resolution of the logging data logging tool is 0.00001. So they're definitely not in the error bar of the measurement. So it's pretty convincing data suggests that interval is the active fault or by the shear swing.
We have another peak. Looks like it's going up
It
60
is,
meters.
you mean that part?
Far right.
Actually, they modify this later because they have to drop down a little bit.
Okay.
Yeah. So they just show one data here. So from this evidence, we suggest that strain is localized at depth because the black gouge is pretty narrow compared to the gray gouge and the wide zone in the outcrop. And we also found some frictional heat in the borehole core. So what I'm doing is try to characterize the clay mineral assemblage through the fault zone. So based on this publication in Nature, Conforma has documented this black gouge as the principal slip zone of the earthquake. And she also tried to estimate fracture energy relevant to the fracture energy percentage of that earthquake. So what I did is try to characterize the clay mineral. So in this data, we did 100 samples from top to bottom. And the mineral assemblage is within the interval in the gray area. It's like this. But if you look at the depth over here, the blackout, you will see the clay content decrease a lot. And then clay mineral assemblage is totally different from other mineral assemblage. And I can explain that later. We found a lot of smectite come out. And at that moment, smectite are commonly considered as a transformation phase from illite. If you have weathering or you have some fluid rock interaction. But in this case, it is not. Because if you have smectite transfer from illite, you need to have a mixed phase called smectite illite mixed layer, so BC. So in this case, I also observed the mixed layer phase in the outcrop of the clay mineralogy of the sample. So in this case, we do not find any mixed layer in between. So this is not the case. Illite is not the source for smectite. In addition, we found some amorphous material. You can mention, you can think that it's a kind of glass. And we determine this with TEM and SEM. You can see some vehicles. They are come from volatile gases come out from the glass. So I make a simple explanation for our observation. So we do have TCDP core, and during the GG earthquake, you have frictional heat. So low melting temperature clay got thermal decomposition. And illite, compared to other clay, have a little bit higher melting temperature. It's about 9 to 1000 degrees Celsius. And kaolinite chloride have a lower melting temperature. And then during the quenching, you have frictional heat, but you also have fluid within the fault zone. So the fluid, hot fluid mixed with glass, will transfer the glass to smectite. So actually, there are a lot of lab study showing the glass smectite transformation, and they are also that kind of study are relevant to nuclear waste deposit. So this quite common in the lab. So that's why we observe smectite. So So the new growth of smectite and some residual of illite is the consequence we observe at the active fault zone. So that's what we observe. This kind of assumption has two weaknesses. The first thing is, in that moment, 2009, no lab experiment can produce gouge melting. That's the first weakness. Rotary shear can shear gouge, but they cannot produce gouge melting at the moment. And the second weakness is, although I mentioned glass can transfer to smectite, but probably you should find some middle phase between growth and the intergrowth with smectite. But luckily, Jason in GFC found that thing, and we shared the material to him, and he published that paper. And hand conduct gouge experiment at high velocity and high normal stress, and then he can produce gouge melting in the lab at the moment. So in our case, or in TCD case, we document that the gouge melting occurred during the earthquake. So just similar to the gouge, the rock melting melt in the Shudo Takeda case. We try to say something about gouge. So after we determine that process, we try to use that process to retrieve some earthquake physics parameters. For example, this process may be localized in a specific interval. So we use synchrotron beam analysis to, point by point analysis, and we obtain 2 points with smectite ridge in that same section. So we suggest that the glass or diversification or SMAC type enrichment is localized in a specific interval. So this interval is suggested as the thickness of the principal slip zone. So in that case, thickness of the principal slip zone will be relevant to the estimation of fracture energy. So we confine the fracture energy to 2% of the earthquake breakdown work energy for this case. And then we also do some tomograph of the melt rock. So this is this sample is from rock cylinder, and we melt it by rotate shear experiment. And after experiment, we try to check the tomographic image with the natural thing. So the upper part is the product from the principal slip zone, and the lower part of the image is the product we observe after the experiment. So you can see this grain size is grain shape is pretty rounded, often rounded, and they are relevant. They are due to Gibbs-Thompson effect. So you have a high ratio. You have angular shape. You will be easily melted in the surrounding by the surrounding melt. So the shape will become rounded. And then we also try to know what's happening during the melting process. So we try. This is another case, and we always try to know what happened during this process. So we will do slip stepping experiment. So we try to do one whole experiment, and we start several experiments at different slip, and then we try to see the tomography evolution and try to know what happened. That's what we can do for now. So it's kind of pity that we cannot have in situ observations through the process. And we also use some neutron to observe the clay fabric orientation. So we use a bulk material. It's pretty thick, and we don't pulverize it into a powder. We just analyze directly with in situ with neutron, and we obtain this kind of clay fabric to refer to in situ stress state. Because in that case, we proposed thermal pressurization was occur in hole B, because for hole A and hole B, I removed that research finding in the end. If you are interested, we can talk about it. But for thermal pressurization, they can reorient the clay fabric, and the recompaction of clay will be relevant to in situ stress state. So let's jump to the rock friction experiment. I just mentioned in 2009, or maybe 5 years later, we still can share gouge with Teflon slip. So I just show you that for rock samples, you use 2 cylinders and you share and push. But for gouge, you can see that it's a 2 rock cylinder, but you have to sandwich the gouge powder with Teflon slip. So in this case, the sample cannot shear at very large normal stress because the gouge will have extrusion because Teflon slip is not very tight. But if you want to reproduce something similar to principal slip zone, you have to shear gouge material in a very large displacement. So you have to shear all the time, try to produce more frictional work, okay, power density. So that's why when I came back to NCU, I tried to develop some pressure vessel. I tried to increase normal stress to mimic the real faulting process. So this is the design I have. So I try to make gouge shear under high normal stress. In the same time, I also allow fluid can drain out or cannot drain out during the experiment because water can play a very important role for frictional behavior. So this is the the GIF image to show you what we have done, what we are doing for our gouge experiment. So we share kaolin because kaolin is a commercial product. So we try to do it, try to realize fluid drainage effect during seismic slip. So for undrained condition, we just published this paper last year. For undrained condition, you share for 7 meters, and we also do the modeling, sorry. And you can see that you have a peak friction and drop down to steady state. And the temperature will increase up to more or less 300 degrees Celsius. And the pore pressure is gradually increased. So very high pore pressure will make effective normal stress low. So that in that case, thermal pressurization is the proposed dominant weakening mechanism. So all the friction drop down because you have high pore pressure and low friction. And after experiment, we do TEM. So all the products have very well crystalline. However, for drain condition, you have peak friction, but you see that it shows a little bit complicated friction behavior. You drop down a little bit and it goes strengthening. And for the temperature measurement, you see some temperature drop during the experiment. And it is very weird because, accumulate frictional power density should generate temperature increase. So that's something we are interested in. And after experiment, we found this amorphous material was obtained. So we do slip stepping experiment. So you can see there are 4 experiments I plot together over here. So they are pretty, replicated. And I will stop over here, over here, over here, and over here. So for all the products, you can see the product state C, here is the state 3, state 4. You can already observe some amorphous material when the frictional behavior goes strengthening and the temperature drops down. And at that moment, we realized that thermal decomposition of kaolin is a very strong endothermic reaction. So when the kaolin thermal decompose, they will absorb a lot of heat. So the principal slip zone temperature will drop down in that case. So that's that is the one of the most important finding. And the second thing is we try to know if normal stress can make influence on the frictional behavior or the process. So we do different kinds of normal stress from 2 megapascal, 5, 15 to 80, because we have pretty good sample holder, and we determine all the product. So we realize the thermal decomposition of kaolin can occur at different displacement, and this seems to be relevant to normal stress. So we plot that with normal stress and our displacement. So this is the displacement to have temperature drop over here. So we plot everything. So we realize that if you want to trigger thermal decomposition or frictional melting, if the low normal stress is not preferred to trigger that things because the power density is very low. So this kind of finding can explain why we cannot obtain frictional melting evidence in the outcrop, even though you share for 10 meters.
Are these experiments done at the same speed?
Yes.
Okay.
Yes. Same speed, but with different displacement. So in this case,
Because the outcrops don't have high normal stress, because you're near the surface, is that what you're saying?
yes, low normal stress.
Yeah.
Low normal stress. So low normal stress, you have to share so for large displacement. But once you have higher normal stress, the strength localized and the frictional power density can be generated easily. So I plot here, and I also plot other geological evidence showing some high temperature features in this plot. So this kind of evidence showing, okay, if you want to have very high frictional heat features in the borehole core, you need to go deeper. That's what we found in this study, and they're also relevant to the power density. So what we learned from TCDPs, we realized strain localization happen. So if you want to obtain some earthquake physics parameters, you probably need to drill a borehole instead of outcrop. And of course, frictional heat and the thermally driven process are all at depth, significant at depth. And in TCDP case, we found gauge melting and the thermal pressurization. The third point is the principal slip zone is the consequence between the slip zone and the surrounding rock. Because you have fluid drainage, that means you have a mature damage zone, which allow fluid can drain out during seismic slip. So that's a pretty important thing. But for TCDP-B, the upper and the lower bump or surrounding the principal slip zone is the clay gouge. So gouge has very low permeability, which will sustain this pore pressure during the course seismic slip, even though they are only away for 50 meters apart, but you observe totally different geological features after an earthquake. So that's something we found from TCDP. Okay, for Wenchuan, that will be very quick. Sorry. It's Wenchuan earthquake, and we collaborator Haibing has 4 borehole, and I mainly work on borehole 1, the first borehole, and he has recognized the principal slip zone at 90 meter at depth. So we went there and we collect sample. We do rock friction experiment, just what we did for TCDP. And after experiment, we found there's a reflective shining surface. And we also determined the principal slip zone with synchrotron. And we realized that graphite was formed within this principal slip zone, but other part are carbonaceous material. So that's the first thing we found. So in our geology paper, we mentioned the graphitization process occurred during the earthquake, and we also checked the principal slip zone of the borehole, and it seems similar in this case. So we suggest the Wenchuan earthquake drove the graphitization process, and graphite is a pretty stable mineral. So in this case, we suggest that if you determine graphite, probably you can obtain some number of past big earthquake because graphite is pretty stable. But
What was the rock type here? Is it like a carbon-rich shale or something?
Actually, this is carbonaceous material bearing sedimentary rock.
Okay.
Yes. They have a lot of core formation in the outcrop. Yes. But after that paper, I realized it is be risky to mention that if we only conduct experiment under very high slip rate. So in the second paper, we try to slip at high velocity and low velocity to see if low velocity can generate graphite. So that's the research topic. So this is a Raman spectroscopy. So we use Raman R1 ratio is D1/G, and you can see the left panel here is the D and the G. So if you have higher temperature, the defect band will lower down, and the graphite band will grow. So once you have R1 ratio decrease and graphitization process degree will increase. And I use Raman because carbonaceous material is Raman is very sensitive to carbonaceous material. So that's why I use this in this study. So we do rock fusion experiment, and this is a log curve, but all you need to see is you need to take care is that we do fusion experiment. It's seismic here under room humidity, and the temperature goes high from the very beginning to the end. Others, of course, they can hide, but just in a very short period of time. So we do Raman, and for R1 ratio is the solid material, and after experiment, either low or high velocity, you can see there's the change to a low R1 value. But if you compare the FWHM, what we said high maximum, you can divide into two groups over here. The first one group is here, and the second one is here, compared to the starting material. For the upper group here, this low temperature part, we determine it with 50 and we cannot find any graphite formed after experiment, no matter which kind of condition. But for under room humidity, high velocity experiment, we found graphite was formed. So in this case, we suggest that gravitization process here can only occur at seismic slip rate and less water. And that is a very important thing because water is everywhere underground. And during shearing, if you have mature damage surrounding the principal slip zone, you can allow co-seismic drainage, and then you can produce something preserved in the slip zone. So we compare that with the natural observation first, and it seems very similar trend. And another paper in Science showing there are really co-seismic fluid drainage during or after earthquake. They do the water level measurement for a long period of time, and they realize that after earthquake, the permeability increase and drop down. So in this case, we suggest that gravitization process are triggered due to fluid drainage. And because this is a 2017 papers, at that finding, I decide to develop such kind of sample holder. So that's why we do something for the gouge for TCDP. Okay, so that's the WFSD case. So we have gouge gravitization. That's the thermally driven process. And graphite could be a seismic indicator. And the third one is the same. PSD is the result of the competition between slip zone and the surrounding rocks. So what we have done, if you realize what we are talking about different kind of slip ray and try to mimic. So we have to increase normal stress. So in this case, you can split roughly for two parts. One is earthquake nucleation and one is earthquake propagation. So before I go back to NCU, they share gouge experiment and very low normal stress, 1 megapascal, and this pretty good apparatus for landsliding, rock landsliding. But after we go back, we design a sample holder here. It's for gouge, high normal stress, and the fluid drainage condition. So we have a lot of work come out, and several work we will submit next month. And we also develop triaxial apparatus, try to obtain some very fundamental but important parameter. For example, random state friction, and or there are numerous that already did this kind of work, but we try to just mimic their process. So that's what we have done. But important thing is I just got a funding, huge funding. So we try to develop a new gauge sample holder. And that sample holder allow us to increase normal stress up to 100 megapascal. And the pore pressure, 70 megapascal is the limit. It's the limit of the ISCO pump. And we also try to set up the fluid drainage, and temperature can up to 450 degrees Celsius. And that kind of condition is designed for very high thermal gradient area. So we already apply this pressure vessel height to Taotan volcano. It's a volcano in Taiwan, and we already apply this to different thermal gradient and the seismicity distribution. So it's quite interesting stuff. And recently, Yaolu in China, Beijing, already published a paper in PNAS, and they report a detailed schematic plot of the height. So I just show you here for reference. So we have very, very, very similar apparatus and sample holder in this case, because all the design, we share the same designer, Toshi Shimamoto. Yes. So the take-home message is, during project provide opportunity to investigate slip zone characteristic, frictional behavior and process. However, it's pity to me is that we never can determine the process involving seismic slip during the, and the response to the frictional behavior. What we can do is we do slip stepping experiment. We start and we check it. So that would be a very important thing if you guys can work on that kind of topic, and that would be fantastic. So that would be my last patch. Thank you very much.
Questions, anyone?
Ready to set up. For the new setup, what's the torque?
Poker?
Torque. When you rotate,
Yes.
you need a torque.
Yes.
What's the maximum torque?
We measure torque. We don't know how much torque we can apply.
Typically for your experiments, what kind of torque level you're applying to the samples?
To be honest, I don't know.
Okay.
Yeah.
And for us to design a new vessel, we need to know that.
都把 estimate from the the radius of the cylinder and the friction coefficient.
Do you have a torque cell built inside along with in the sample?
Actually, we have we have a lot of clock over here. So it just give a current and it just share. So we measure torque over here. So I'm not sure what you're talking about torque, but I know.
Torque is force divided multiplied by the distance, right?
Yes.
And for typical stick slip experiments, that's a very important parameter,
Yes.
because you need to know how much torque you get it, and all of a sudden you lose that torque, and so you get a slip.
Yeah. For torque measurement, for torque control or torque issue, that would be highly relevant to triaxial apparatus and
experiments.
but for rotary, we have no at least to me, I don't have any idea about how much torque.
Yeah, your stress is basically just get it going.
Yes. Yeah. So we just force it to go.
Yeah.
And we measure the torque over here. And the torque will transfer to the shear stress. Because we have during the sharing, we have force and anti-force.
Mhm.
So when we share, they have something to try to rebound.
Yeah.
So we measure that torque,
Measure that torque, okay.
and we change. We convert that torque into shear stress.
Okay.
It's a
Yeah,
shear
yeah.
So we do not have constraint of the torque we apply. We know how much velocity we apply.
But
As
the thing
a-
is balanced, so how much torque do you have at the bottom?
The torque
Yeah.
on the bottom is relevant to how much normal stress you apply.
Sure.
So
Okay.
yeah, so I don't have any. I don't have a correct number for you.
Okay.
Yes. Any question?
I'm curious how tall that whole setup is.
It's about
Entire thing.
2.5 meter
Oh, okay, that's
higher.
Interesting also in the tomography images. Can you go back to the movies in there?
This one or this one?
The top and bottom one. Yeah, this is the one. So this is these movies are basically cut off the rest of the images, right? So this is only part of the
Yes.
entire
Yes.
movie.
Yes.
So there's a lot of overlap. Some features may coming in and moving out. Because as
For the left part of
the right part.
the right part, we use that as a tip sample. So we use a pin to stick a melt from the center,
Yeah,
and then we
yeah.
rotate it,
Yeah.
and we construct in 3D image because we rotate.
So it's a cutaway section, a little piece of a
Yes.
sample that you've extracted.
Yes. Yes.
Do you play this again? Because I see something moving in and out.
Because the geometry of some sample is
So the real field of view is much bigger than this.
Yes.
The real image is much bigger than this. Yeah, okay. And these round features,
the round one.
yeah, are they bubbles or?
No, they are quartz.
Of course, that's been
Course,
melted, so it
right.
became round.
Yes. Because that's why we tried. That's why we compare with the original one because of course it's sandstone, but it's not completely rounded. It's you are subangular to subrounded thing. But when you have high temperature melt, it subangular or subrounded thing will become very rounded because of gypsum effect. Yes, so the very sharp angle one will be melt easier than other flat surface. So that's what we interpret.
When we've done coarse tomography, is you rotate a sample 180 degrees. Sometimes your grain may be in a diffraction condition and the grains will turn dark.
Turn down.
And it goes brighter and darker and as you rotate.
That's a diffraction.
Yeah. The question is, I don't see this change.
But this is you don't see that in the reconstruction. You only
Oh,
see
that's
that
right.
in the radiogram. And this is a reconstructed.
And we use this as it's called TXM, transmission X-ray microscope.
Okay.
So if you enlarge the tip sample, the sample have different thickness. So when you rotate, you will have sometimes you have very
So
clear.
what's the scale? What's the horizontal field of view?
Yeah, that's very.
That's one. Or
Yeah. No, on the right.
this one. Probably 1 micrometer. Or yes,
What millimeter?
one micrometer.
micro.
So this is TXM.
So this is nano.
This is nano.
Yeah,
These
yes,
are very
very
small. Okay, that makes sense.
Yeah. So that's a tip one. Yes.
very small.
So we make rock slice like this, and we collect very tiny one to make penetration, make X-ray penetration.
Yeah.
So we also collect the one from principal result. So we found out that cores are melt very rounded in that case. So that's why we suggest gouge melting happen, but maybe some rock also melt in that case. Yeah.
Where's that TXM?
National Synchrotron Research Center, something, NSRC in Taiwan.
In Taiwan. Okay.
Yeah. And we apply this image, a technique to Fuggerite and other stuff, because Fuggerite is kind of product from extreme energy event. Extreme, yeah, like high temperature and high pressure. So, yeah. So that's what we have.
Well, the grains are really, really tiny.
Yes.
I have a general question. Say if you can bring your apparatus to the beamline, what is the most important information you would like to get if you can do in situ work?
Oh, okay. Let me go back to please. No. This is the most important thing. Frictional power density drive thermally active process, but the process associated with the mechanical response remain very subtle. After discussion with Yan Bin this morning, I realized that if you can have some in situ observation for some weakening mechanism, that will be awesome. And one of the important weakening mechanisms, flash heating. David Goldsby have a science paper relevant to flash heating, and the temperature. The velocity for flash heating is not 1 meter per second. It's only 45 or 40 millimeter per second. You see a dramatic friction drop. So they share rock, different kind of rock. They see this flash heating and the weakening mechanism. So there's a dominant mechanism and almost used for every kind of material. However, I gotta say, no one report flash heating evidence because it is initiated in the very beginning, and then later on, other process will overprint these things. So if you have technique to detect the flash heating, there's a several seconds, and you can see some asperity melt. That would be awesome. We used to use the flash heating as a how to say fire starter, saying flash heating, so you have frictional heat, and the water can absorb that heat, and it got expansion and thermal pressurization. So everything starts from flash heating.
What's the magnitude of the temperature jump in the flash that it requires to?
From several modeling paper, they suggest the temperature can up to 2000 K.
Okay.
It's pretty high, but in science paper, they mentioned, you cannot measure that temperature because this occur in the asperities. So after experiment, during the experiment, you can barely measure the temperature increase.
Right.
So it's a pretty tricky part.
Can you help the process by artificially heat the sample?
What do you mean artificially heat sample?
During the friction experiment, let's say you're at room temperature, but in the moment I drive a current through the heater, give it 1,000 degrees.
Yeah,
cheating.
It is cheating, but
yeah, it's
humans cheat all the time.
but flash heating is very
But you want heat to be localized.
yes, because very, 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 it's up to several micrometer. That's what they propose.
Micrometer?
Yes, because asperity is very
But
Yeah,
you put it,
You can
there's a
put
going
vertical
wide, going crazy. You can have a 10 micron tungsten wire in the sample, right? And all of a sudden you just strike the current.
But
through it.
if it is flash heating is driven by asperities, you can artificially make the rate. So the radius of curvature is driving, right, in some sense. So you can actually artificially make or
roughen your rock samples, and you can take differential, like, you have something with very high radius of curvature, something with very low radius of curvature. And even if you can't measure the temperature, your response will scale according to your radius of curvature.
Ah, okay. Okay. But that's still from experimental approach.
Yeah, because if your thing just dissipates very fast, unless you use some other technique, it'd be very difficult to.
Yeah, but for flash heating experiment, I gotta say that.
It's like lightning, essentially.
Yes.
Except not in the gas phase, but you're working in the solid phase. That's the problem, right?
Yeah. But what I'm saying is that we cannot see flash heating. We can see for example, we cannot see thermal pressurization, but we can see melt. Melting over there, right? You see melt.
And
And
a laser shooting at the edge of your sample, and then you get.
No, I think you must do the
radiation.
experiment which mimics because it's a self-generated process, right? Something is appearing against something, and the interface is generating this kind of lightning or whatever flash heating effect. So if you artificially either dump heat in that would be kind of counterproductive, right? It's
It's a simulation.
that will completely screw up the physics.
Essentially, thinking run is actually your starter.
It's like trying to start a fire, right?
Yeah.
Of course, you can use a laser to start a fire, but the whole process of
No.
lighting a matchstick is
Want to
not.
locally trigger it. So the rest is still cold, but only one spot is hot, and this spot once you start, it's gonna trigger the rest. So it's a simulation. It's not a.
Oh, I see. Okay.
Right. Well, I mean, we don't know.
Yeah.
Right?
So it's like a dielectric breakdown, right? You're doing it, and then you have that.
yeah, but yes, to me, flash heating is pretty easy to use, but difficult to document. You use it, the paper will not be rejected, but then you don't use it, it will reject.
Because nobody can either
Yes,
prove it or
yes,
reject it.
but already prove it from experiment.
You
Yeah.
can prove it.
You don't have any transparent rocks.
Some they use glass, but for the glass they are trying to mimic earthquake nucleation. They put a lot of sensors, but they don't push it with
So why
high.
can't you do it? Take the same transparent like glass and.
They yeah, I'm not pretty sure. I'm not good.
That would be the easiest way to, and then you just use fast camera.
Okay.
Some photosensitive plastics.
On the other side, I mean, your detector doesn't have to be a conventional detector. I mean, you can also take any detector which up converts or down converts the light. So.
Thank you.
I'm gonna give too many suggestions.
Thank you very much.
Thank you.
Thank you.